Okay, so today we are going to continue our discussion about using neural networks for natural language processing. And today we are going to look at the language models again. Remember our previous discussion about the language models? We said that given any sentence, w1 dot dot wn, I can assign a probability for this sentence. This is a statistical language modeling, probabilistic language modeling, and this would be very useful. Why? Using this probability model of the language, I can generate new sentences, or given a sentence, I can say that if the sentence is likely or not likely. Today we are going to do the same thing, language modeling, but this time it is not through the statistical language modeling, but this time it is through neural language modeling, okay? Language models, neural network-based language models, and it is called not statistical language model, but neural language model, okay? So let's get to it, okay? So RNNs will be the ones that we are going to use for one-dimensional data actually, but it will be mostly used for natural languages. Okay, so let's look at this one. I kind of talked about this last week. Maybe it wasn't that clear, but we don't have to understand everything just to use it. Remember, this is something that we say, let's ignore this part now. Let's ignore this part now, what regularization is. This is something that we optimize. This is called full loss function, okay? And if you remember this, E, F, Y, I over all the classes of E, F, C. So this is E to the power something. FYI is the score for class number I, okay? And if I take the e to the power that number, that's going to be a plus number, greater than 0 up to infinity. These are all the scores for all the classes for the given input. And if I add them up, this division should be between 0 and 1. For the correct class, if I take the minus log of it, due to some reasons that we talked about last week, and if I add up all these numbers for the correct classes, I will get the loss. Loss is the total error that I am doing, that I am getting for my whole network, for all of my data. Let's say I have 1,000 different labels for my data. What are my labels? I think maybe I should talk about them by going to last week's. Okay, let's do, instead of looking at all that data, no, not this one. I am going to use this one. Okay, PDF, yeah, okay. So remember, that's what we were looking at, the named entity recognition. Somebody sat down and marked each of these words as like other or organization or miscellaneous or location or person or date or etc. So each of these words in my corpora has a label, okay? Label is organization, other, miscellaneous, location, person, date, etc. So total of maybe 8 classes, okay? Total of 8 classes, and this is called named entity recognition. So we are kind of trying to find the names, okay? Named entities. We are trying to find the names in a sentence, and we are going to classify them. For example, European Commission is a name here, German is a name here, Fisher is a name, Britain is a name, France is a name, National Farmers Union is a name, etc. Find the names and classify them. That's the problem. And for that one, as you see, so given the sentence, these are organizations, this is other, okay, or a person, organization, other, and etc. This is an important problem. Why? Because we talked about it last week. I'm not going to talk about it again. So I am going to show you this. Okay. So if each word is represented by a word to vector, okay, let's say, just to keep the thing simple, unrealistically it is 5, okay. Each word is a 4-dimensional vector. Okay, D is 4, okay. I have 5 of them, 5 words, and I like to classify the center word here, Paris. Is Paris a name? If it's a name, then what kind of name it is? Is it location, it is person, it is organization, and etc. Well, you might say that everybody knows that Paris is a city name, it's a location. No, it may not be, because sometimes people use Paris as a person name too. Okay, I wouldn't know that. And sometimes maybe there are organizations named Paris. Okay, sometimes, for example, the Good People of Paris organization. Okay, in that case, that word Paris is part of an organization. I cannot say it's a location all the time. It depends on the context. This was the problem. So I am going to give you this 5 times D. D in this case is 4. So 5 times 4, 20-dimensional vector like this one. And I am going to ask you to give me the named entity recognition label of Paris. That's my problem is. Okay, that's my problem is. So I think this is what I'm going to do. If I'm going to use a very basic linear classifier, this is what I am doing. See, if let's say I have 8 classes, okay, classes are from 1 to 8. Class number 1 is other, class number 2 is person, class number 3 is location, and etc. I am going to test all of these classes one by one. The weight of the classes of that class times my input. My input is 20-dimensional vector, and I'm going to do all this calculation for all of them. So it's kind of like this, right? I have a matrix. For example, this is my first of all, this is my 20-dimensional vector. Okay, there are 20 numbers in it, and these numbers represent this. Museums in Paris are amazing. Okay, and I am going to multiply it with this matrix. Okay, this matrix is, okay, of course, each line, each row here should contain 20 elements, right? Each row should contain 20 elements. How many rows do I have? I have C number of rows, okay? Class number of rows. So doing this calculation is kind of doing this matrix multiplication, and doing this probability is dividing this multiplication by the addition of all of these multiplication. Of course, they should be taken the exponentiation of, and calculating this probability. That will give me, okay, given this vector, this calculation, this softmax calculation is going to calculate my probability assignment for each of those classes. Again, because I am doing this division, I cannot produce anything smaller than 0, because e to the power something is always larger than 0, and it cannot be larger than 1.0, because this one is y has to be between 1 and c, and that cannot be greater than 1.0. It could be at most 1.0. That's a probability assignment. That's what I'm saying. So the important thing here is that find all of these W values. Okay. How many W values I have? C times 20, okay, inside this matrix. This is only during the runtime, during whenever I get a sentence like this, I ask the same question, I get a class back. But this is the loss, right? What is loss? Loss is put all the things that you have marked in your data set like this, okay? Like this, okay? Given the database, data set that you have marked before, okay? Foreign ministry spokesman, Shen, etc. The center word is a person here. I know that given 5 word, okay, 1, 2, this one, right? This 1, 2, 3, 4, 5. 5 word sentence part. Given this 5 word sentence part, I know that if I feed this in through my network, it should produce a person class. I know this one. And I slide my window. I should slide my window. My window is now, I am going to slide it like this. Now this one should produce another person again, okay? And I'm going to slide this again. Now this one should produce what? This one should produce other, right? Other. Okay? So I put all of them, one by one. I should produce all of those. And I am calculating this loss value out of those, right? Put each one of them. For that person, I am going to put this E here and the rest of them. For the person, I am going to do this. And for the other, I am going to put this. Take the minus log of it and add them up. And that's going to tell me how good my parameters are. I want this loss to be 0. Loss is bad. I want it to be 0, but it will never be 0. If your loss is coming back as 0, you are doing something bad, okay? Although we like it to be 0, but in real life, because of the noise, because of the labeling problems, because of the word vectors and etc., it will never be 0. It will be greater than 0, but I like this to be as small as 0. Okay, during the training, I put all of them, and I start changing my theta. My theta are these, right? My theta are these. My weights. Okay, I change my weight a little bit, and that will improve my. Loss. And after that, I am going to see that it is being improved, and I'm going to do this again and again and again, etc. And at the end, I am going to find a set of W values that will say that, okay, for now, I cannot do better than this W values. Now you can go ahead and calculate the classes for new sentences, okay? That's what I am going to do. That's the whole idea of the neural network or basic machine learning, okay? So how would I minimize this loss? This is what we do, right? This is what we do to minimize it. We say that, okay? Take the derivative of this loss with respect to my parameters. Remember the figures that I showed you? If this is my function like that, in this case my theta is a simple, okay, f theta is a simple one-dimensional parameter, okay, it is x. If I started my x at this position, okay, if I take the derivative of this thing with respect to theta or x, let me make this x, okay. If I take the derivative of this function with respect to x, it's going to give me this slope, right? So what I am saying here is that, take the derivative of this one. That's going to give you a slope, okay? Multiply that slope with alpha, that's the step size, and decrease this theta, this amount. So I am saying that, okay, my slope is this. My slope is telling me that I am decreasing very, very fast. So I should decrease it fast. This is my x. This is my x or theta. Okay. So I'm going to take this much of theta out of this one. So I will be moving like this. Now x is here. Take another derivative. Take another derivative. And this time it's going to be a little bit less slope. And it's going to move me maybe around here. So if I repeat this a few times, I am going to get to a position where I cannot improve this anymore. It will move around that, right? So basically, I will start at one point like here. I will move there, then come back, then do this maybe. Okay? That's called gradient descent. We already talked about this. Gradient descent algorithm. And if I do this gradient descent algorithm on this loss, okay, by the way, in this theta, there are, 8 times 20 parameters. That's like 160 parameters, right? And I assume that, in this case, each word is a four-dimensional thing, okay? Four-dimensional word, but usually I know that each word is a 200-dimensional vector. And if I multiply this with 8 again, now I am talking about 1600 numbers. Lots of numbers. Like I said, it becomes a 1600-dimensional space and 1600-dimensional problem. But the technique is there. We know how it works. Take the derivative of this one with respect to parameters. I know how those numbers are calculated. If I am careful, I can do this calculation many times and adjust these theta values so that I know that I cannot do any better than that starting from this position. Of course we have these kind of problems. What do you call this problem? I am going to show you a problem. I have a function like this. Function is like this, and I started at this position, right? My x is here. I started at this position. This is going to be my slope, right? I will end up around, okay, I will start at this position, then I will come to this position, then this position, then go there, and I cannot move out of that position anymore. What do you call this problem? Local minima. Local minima, right? Local minima. Local minima. And local minima, local optima, is the biggest problem of gradient descent applications, gradient descent algorithms. I mean, but I cannot solve this problem because if I am stuck on a local minima position, I will stay there, and there is no way. If I don't do anything else other than the gradient descent, there is no way that I can move out of that local minima. Okay, that's the problem with the gradient descent. But people are smart enough; they say that, okay, let's modify gradient descent this way and this way and this way and this way. For the new starters, I usually refer them to Google's neural network playground. Do I have? Yeah. TensorFlow Google Network Playground. This Google Network Playground is a very simple, okay? So, let me make this Hidden layers, okay. No hidden layers. Okay. So I have just two inputs. Remember I had 200 dimensional words and I have 5 words. 200 times 5 is 1000 dimensional input. In this case it is just 2-dimensional input. And I like to be able to classify such a 2-dimensional problem. Remember my 2-dimensional problems? What was the problem? Price versus the square meter of a house, right? Price versus what? Price versus the age of a car, right? That was the thing. Maybe I can do, well, yeah, it's okay. It's like that, right? If your problem is like this, okay, let's say this is my price and this is the age. I like to buy these kind of cars, right? Price is low, age is low. I don't want to buy these kind of cars. Price is high and the age is high, right? So I like to write a classifier given 2-dimensional input, price and the car, age of the car. I like to be able to say, okay, buy it or not buy it. So these are my training data, and I like to train my neural network, which has just 2 inputs, and I say that, okay, find me a line that divides this space into 2. So basically what I have is just try to draw it. So basically it is this. This is my node, this is my input, price and the age of the car, right? I get this, just a single node. This is W1 and this is W2. I am multiplying this P with W1 and A with W2. So P times W1 plus A times W2, that means what? W1, W2 is a matrix and Hocam bugün müydü ya şey? Ben salı günü sanıyordum ya. Hiç kimseye haber vermedim bile ben.
Salıda mı gelelim?
Kaçta 2'de mi başladınız siz? 3'te başlayacaksınız. Siz devam edin hocam, benim bugün dersim var ya. Ben yarın sanıyorum ya. Tamam. So today is Monday, right? At least I know that much. I thought their classes are on Tuesday. So P and A, okay, that's it. That's what I am going to do. Just find these 2 numbers. This is for buy, the other one is not buy, but I am not going to make this complicated. So find these 2 numbers, and those 2 numbers will give me a straight line to divide it. So just try each of these on this W1, W2 thing. At the beginning, I am going to, okay, see the current weight is minus, okay, this one. It is, current weight is, how am I gonna, okay, I can move this out, yeah. I can change the current weight to 0.5, for example. That's my initial weight. For this one, my initial weight may be minus 0.5. I gave the initial weights, and it is doing this. It is not classifying it in a right way, but I put in the gradient descent and I say that, okay, optimize it. Okay, it said that, okay, I am going to optimize it this way. It looks like my training loss is becoming 0, which is a perfect data because that's a very good data. I can nicely separate these 2. And my weights become 1.3 and the other one is 0.75. Gradient descent run. Stop it and let's add a little bit noise to our training data. Let's add more training data. So it looks like there is no way that I can separate these 2 data using a straight line. So loss will never be 0. Okay, optimize it again. It is optimizing it. As you see, loss is becoming smaller and smaller, and the line it is drawing is not bad, but as you see, there is no way that a line can separate this and this and this. I mean, these are not hopeless, right? I cannot do that. But I am still doing okay. I am still doing okay. Loss is like this big. Okay? What is epoch? Epoch is this. Epoch is every time I run this is my gradient descent. I run this gradient descent for the whole data set. How many points do I have? How many points do I have? I don't know. I think maybe 1,000 points, 500 blue and 500 orange points. Okay. If I run my gradient descent program through all that points one by one once, that's called an epoch. So this is running its second epoch, and well, it's not going to go anywhere. Let's pause it. Okay.
So 2000.
What?
I think it's not second. It's 2188.
Really? No, it is epoch 2.188. Really?
Thousands. It's thousands, sir. Because decimal separator is point here.
Really? Oh, okay. Maybe I was wondering why it is taking so. Why is that taking so much time for a complete epoch? So it is either 2,000 times or 2.188 times. Doesn't matter. The epoch is going through all of your data once is an epoch. Okay. So maybe it was a good thing. Maybe I added too much noise. Let's make the noise a little bit less severe, and this should be okay now. Okay. It calculated it, and my losses that way and training losses that. But okay. So what is the test loss and what is the training loss? Can you guess? Okay, let me show you test data. This is my test data. This is my test data. Okay. This is training data. So when I am training my network, I don't show this test data to it. So my training happens without saying any of these, okay? The circles with blue, with the black circles, okay? So this is a black circle, black circle. Black circles are my test data, okay? Test data is never shown to the training process. So that's why the loss of the test data and the training data is different. And of course, you would expect your training loss to be smaller than the test loss, because you are optimizing your parameters with respect to the training loss. Okay, that's what we are doing. If we can, let's do this. Okay, if we try to separate this data into two, okay, by the car or not by the car, let's say our data set is like that, okay, there is no hope that a neural network like this, a line separation, will do anything like that and say that test loss is 0.5. It's just random numbers, it's just a throw of a dice. I mean, the worst that you can do with the loss is 1.0 in this case. The best is 0.0. So I cannot find anything in this one because I mean, my network is too weak, too unpowerful to capture the data in this one. For that one, I need to add some more steps like this. So what do I mean? Internal hidden states, like put this one in there too and get the outputs of them, and this is my output. So it's going to be more weights to it. W1, W2, W3, W4, W5, and W6. Okay, 6 parameters now. I need to optimize 6 parameters, but this one will draw a line, this one will draw another line, and this one will take those lines out and it will make a decision out of those lines. So if I do this, let's optimize it. See, two lines there, right? One line and another line. It looks like it did a decent job, right? It did a decent job. I think one line comes from the upper one, the other one comes from the lower one. The third one only can say that whatever remains under the first line and whatever remains over the second line is going to be my solution. It looks like my training loss is now, it's not 0.5, it is 0.2. Other than these orange stuff and orange stuff here, I am doing not bad, right? I am doing okay. So how would you go in terms of, say, this one? This is one line, this is another line, one line, another line. If I combine these two, I'll get this. So how would you go designing your network? I would say that I'm going to add another line here. Okay, third line, maybe a fourth line. So four of them will make kind of a rectangular stuff. Maybe I can capture it in this case. Let's move it again. See, not bad. So you might say that, well, these are not lines anymore. No, it is see, this is a line, another line, another line. If you take the weighted average of those lines, you get these nice stuff. And it looks like I didn't need this, right? This one is just producing just blue. If you get nice weighted average of these three lines, your training loss is going to be this. Okay? Adding weight layers before the result layer definitely will make your neural network stronger, definitely will make your neural network more powerful. But with the power comes the price. What is the price? More number of parameters to tune up. Okay? More number of parameters to tune up. So this network is powerful enough. I think 3 of them will do fine. Yeah, 3 of them will do fine. Good. But that's not going to be fine with this kind of a data. Right? No 3 lines can separate it. Let's try to run it again. Let's see what's happening. Well, it's not moving much. It's not moving much. Something is happening, but my training loss is 0.4 again. You see this curvy thing here? Can I make discretize out? Yeah. So 3 lines are trying to interact with each other. Do you see what it's doing? Trying to capture this part, but I cannot capture this part. So 3 lines are not going to be enough for this one. Let's add more neurons. Let's try to optimize it. It's again around 0.4. See this one creeping in? There is an island there. It's going very, very slowly, but it is doing okay. This test loss being better than, see, it started test loss is being better than the training loss. That means that I am getting is junk. Your test loss should never be greater than the training loss. You shouldn't trust that kind of a result. So it got this one. Yeah, not bad, right? Again, this one is not that good in terms of getting the details of such a data. So maybe I can add one more hidden layer, more neurons, get this one out, and run it again. Okay, so usually it takes some time to find the correct parameters. See, I am doing 2 types of search. One is as a human being, as a user, I am designing my neural network, add more layers, add more neurons. Okay. The second is every time I design the neural network, I make a new gradient descent search. Okay, my network doesn't seem that. I mean, the result doesn't seem that meaningful, but it kind of explains the data. Definitely all fits here. See, there's definitely, I say that there is no orange dot around here, so I am going to make this blue. These are capturing it fine. This one is okay too. So I'm going to see this one all fit. So I mean, I shouldn't have this region here. Again, this region shouldn't be there. But this is my data, and that's how I'm going to do it. It might do something if we wait a little bit more. See the oscillations here? It's going up and down. Why is that doing that oscillation is going up and down? We'll talk about it in a few minutes. Anyways, so play with this, but
Overfitting.
yeah, it's overfitting, but these oscillations are kind of weird. That's because we are doing the stochastic gradient descent. We'll talk about it in a few minutes. Okay, so let me pause this and let me go to my slides again. Okay, so that's what we do, gradient descent. This is just the one that I showed you is just one-dimensional gradient descent. The one that we are trying to optimize is how many parameters are there? Let's see the number of parameters. It's like 1, 2, 3, 1, 2, 1, 2, 1, 2, and 1, 2. It's going to be 8 here, and it's going to be, for each one is 3. 9 is here and 3 here, without including the biases. 8 plus 9 plus 3 is going to be around 20 parameters. So it is making a search in a 20 plus dimensional space. In this case, my search was a single one-dimensional space. There is just one x. What should be the x? What should be the x to optimize this f function, right? So in real life, we will be talking about search in, let's say, 20,000 dimensional space or 100,000 dimensional space, because that's how many parameters we are going to have, right? And those kind of spaces are not visualizable. In this case, since my input is two-dimensional, I visualize it. But if my input is like 200 dimensional, as I showed you before, right, I cannot visualize it either. So all I can do is trust our equations, trust this one. I can take derivatives of any functions, including 1,000 million dimensional functions, doesn't matter, with million dimensional, with million parameters. And I should know that there should be some local minima, and I cannot get away from the local minimas. I have to know how to live with the local minimas. That will be the basic things that we need to solve about gradient descent, or sometimes, most of the time, I'm not going to solve the whole problem. I should know how to live with the gradient descent problem. Okay, so I kept talking about putting all that data. Remember what I did here? I told you that I am going to do this addition for all of my input data. But if my input data is, let's say, thousands of samples, thousands of negative positive samples, doing this calculation is going to take lots of time, and it will not fit in my memory. That's why I don't do it that way. If I have 1,000 samples, I will take random 5 samples. I will optimize my theta for that 5 samples, and optimized data, I will optimize it with another 5 data, another 5 data, another 5 data, until I am done. Okay, since I am taking those 5 data randomly out of those 100 data points available, that's called stochastic gradient descent. That's why we had those oscillations up and down. Okay, So is that guy reading his emails? No, writing an email. You are writing an email? Reading an email? Just turn your computer off. Turn it off, yes. Okay. Since you understood everything, just do you have any comments to make? No? Do you have any questions? Do you have any comments to make? Any part? I'm talking to you. Yeah. Since you were typing something, so did I mention something that is not correct? Okay. Good. Okay. So let's talk about this, and maybe this is a good graph too. Okay. When I increase doing this gradient descent thing, my training error will get smaller and smaller and smaller. Okay. My test error doesn't have to get smaller. Okay. In fact, after some time, this is going to get higher. And I think we have seen see? Exactly. My training error is getting smaller. My testing error after some time, it gets higher. Okay? We don't like it, we don't like this to be happening. It shows that after this point, all I am doing is memorizing my training data. I am not learning it, I am memorizing it. I am trying to explain my training data. If I test my system with the unseen test data, my error is going to be high. And it's getting worse and worse, right? So it looks like if I knew it, maybe I can stop at this point, and say that for this network configuration, it doesn't make any sense to continue any further. Your training error is going to be lower, but your testing error is going to be high. Okay? So this is called overfitting. And that's a typical graph, actually. That's a typical graph. If you continue your training, our gradient descent approach is very powerful. Our networks are powerful too. You will get very low training errors, but your testing error is something different, and this is the more important one. Okay, that's what happened. It just says that your network is too powerful for this data. You are learning your data too much. Sometimes to get rid of this kind of behavior, it is interesting, but you add more noise. When you add more noise, okay, you don't get like gaps like I had before. And if I optimize it, sometimes more noise makes it better. Kind of counterintuitive, but with the noise, with the added noise, sometimes you get better results. I wonder if, yeah.
Is it because it decreases the correlation of noise? Maybe we add extra noise.
What do you mean correlation of noise? What's correlation of noise?
Maybe our model detect correlation in the noise under the data, and if you add extra noise, then that correlation decreases.
Yeah, could be, but in this case, I think I prevented lots of gaps. Remember, I had gaps in the data, and our model was trying to model those gaps. Now I don't have that kind of gaps, and it looks like I am doing better, right? See this one? At least I don't have that error is getting higher for the test case, right? Both training loss and test loss is doing better. Okay, I am not saying that this will work all the time. Sometimes adding more noise is going to help you. That's what I'm saying. Okay. And sometimes we call that augmentation. Doing augmentation is not that easy with the NLP approaches. Anyways, and the other thing is this. See, read this one for me, and after that I am going to give you some break. What is this? Regularization. Don't pay any attention to the name of it. These are my parameters. This is an optimization. I am trying to minimize this loss. This is my loss, and this one says that add lambda times squares of each parameter. So what am I trying to do here? And minimize this whole thing. I understand this part. If this part is small, that means that's my label data. How about this part? What am I trying to do by adding this part?
Also trying to get smaller parameters.
Get smaller parameters. Why? Because my parameter space is so big, okay? I don't want to use large parameters. I am trying to force my search space into a smaller part of the large search space, okay? Keep parameters around 0, don't go away, okay? Interesting stuff is happening here. That's called regularization. And I did not use any regularization. Yeah, I can use regularization. That one is an L2 regularization. Here I am using L2 regularization. Keep small parameters and do it again. I am not saying that it's going to do it better than this one. See, this one is, yeah. Okay, both of them are getting smaller now. This one is getting smaller. Well, both of them are getting smaller. It's a good sign. Again, this is overfit. Here is overfit. Another overfit there. Okay. But I don't get, it looks like I am not going to get anything better than that. So regularization helped a little bit. And these are the numbers. Weights are small, but it is not as small as I wanted, maybe. Okay. Regularization did not help that much. I mean, I think this is the best I could have. This is the best so far I achieved, but I'm not saying that this is the result of the regularization. If you stop this and start again, I'm going to get something different because of the stochastic gradient descent. Okay. By the way, again, these are lines, line, line, line, line. These are combining lines, and the final one is combination of line combinations. Okay. Good. Let's go back to our slides and let's continue from here, but I think I need to take some break first. So let's take some break. 10 minutes or maybe 10 minutes, okay? Ya arkadaşlar geldiğinde yoklamayı hatırlatın bana.
O resmi de açabilir misiniz? Kısa bir şey sorabilir miyim? Gradient destekte overfit yani aşırı öğrenmeleri ben görebiliyorum ama bu resimde neye göre aşırı öğrenme dediniz mesela? O resimde gösterebilir misiniz? Dediniz de şurası
Resimde değil, hayır şurada gösterdim.
Ha burada mı gösterdi?
Grafikte gösterdim.
Şurada göstermediniz.
Orada değil. Ha burada da var, yok hayır bak.
Burada mesela nasıl?
Şurada da var bak. Bu ne bu? Esasında normalde sana verseler ne yaparsın? Sen şu spreni işaretlersin değil mi? İki boyutlu ya, problem görüyorum karşımda. Bu adam burada delik var diye diyor ki sanki ya burada diyor turuncular buraya gelir diyor. Yapmış bunu overfit bu. Çünkü biraz tesadüfen burada bir şeyler yok. Ya da başka yerlerde nerede başka mesela bu. Burada sadece bir tane nokta var diye bunu feda etmiş. Bunu buradan geçirmiş. Anladın mı? Halbuki ben bunun böyle olmasını beklerim. Bayağı overfit var buralarda. Bence öyle. Noise eklediği zaman da buralar doluyor. Noise ne demek? Bunun etrafına bir şeyler koy. Bunun etrafına bir şeyler koy. Bunun etrafına bir şeyler koy. Oradan anlayabiliyorum ama bu oyuncak problem. Gerçek data da böyle gözünle bakıp bunları göremezsin.
Çok katmanlı.
Evet. Çünkü bu 2 boyutlu problem. Bizimkiler 1000 boyutlu problem ve milyon tane parametre optimize ediyor.
Hocam ben şey soracağım bitirmemle ilgili. Delay siliyorum ya. Size bir şey diyeceğim ben. Verimi kendim oluşturuyorum ya ben. Delay varmış gibi davranıyorum.
Evet.
Hocam bence gerçek gelecek veri gibi oluşturamadım. Şimdi şey düşünüyorum. Stüdyodaki yani bir taraf konuştu.
Evet, konuştu.
Diğerine ses geç geldiği için geç cevap veriyor.
Evet.
Ama ben onu düzgün oluşturamadım. Diyelim ki kırmızı alanda konuştu.
Evet.
Bana geç geldi. Yani burada gelmesi
Evet,
gerekirken
ha.
burada geldi.
Aha.
Ben geç cevap verdim.
Aha.
Bu dileği tespit etmeliyim ben, değil mi? Geç cevap verdim. Duyduğum gibi verdim cevabımı ama o geç duymuş oldu. Böyle bir veri oluşturamadım hocam.
Sen bunu video özel sese bakarak mı yapıyorsun?
Yani sese bakarak yapmıştım da şu an böyle değil verim, o yüzden aslında doğru bulmuş olmadım. Böyle gelmeyecek mi gerçek verim benim?
Ne olacak, biz karşıdan izleyen kişiler olarak boşluk diyoruz değil mi? Ses yok.
Evet.
Biri soru soruyor, öbürü bekliyor hala. Şimdi yapabileceğin en kestirme şey o sessizliği yok etmek.
Evet ama ben işte bana gerçek veri nasıl gelecek bilmediğim için kendi oluşturduğum veriydi hocam. Ben sustum.
Bir dakika,
İki taraf da
gerçek veri şu.
Ben nasıl bir veri oluşturmalıyım?
Sen nasıl veri oluşturmalısın? Şöyle, şimdi iki kişi karşılıklı
Evet.
Sen nasıl yapıyorsun? Karşılıklı mı konuşuyorlar?
Evet ama hani siz iki video ayrı ayrı gelsin input olarak dediniz ya. Ben
Tamam.
ikisi
Karşılıklı
tek
konuşturma onları. Sen mesela şey yap ona. Soruyu soran kişininkini kaydet. Tamam mı? Şimdi soruyu sor de ona. O videoyu oynat. Tamam mı? Ama oynat dedikten 5 saniye sonra başlatarak oynatsın.
Tamam, yani konuşsun 5 saniye beklesin tekrar konuşsun.
Yok, soruyu sorsun. Soruyu sormaya başla dedin, tamam mı? Sen başla dedikten sonra 5 saniye beklesin, ondan sonra soruyu sorsun o kişiye.
Tamam.
Sonra da senin soruyu sorduğun andaki video belli. 5 saniye sonra ona gittiğini simüle ediyorsun. O da cevap vermeye başlıyor. Arada bir 5 saniyelik boşluk olması lazım geri gelmesine.
Tamam, bu şekilde olacak yani o geç duyuyormuş gibi. O zaman
Ne çizdiğini çok bilmiyorum ama şu kırmızılar
hocam.
senin sordukların mı?
aynen bu sordu.
Evet.
Buna sorduğu anda gelmedi.
Gelmedi,
Şu 2
evet.
saniye geç duymaya başladı. Sonra ama
Evet.
direkt
Sen
ben
bunları şey olarak yapsana, izafiyet teorisi falan filan gibi. Duyan kişiyle, tamam mı? Soru soranın şeyleri farklı. Timeline'ları.
evet.
Yani bir bunu onun için çizeceksin, bir de onun için çizeceksin. Soran kişinin duyduğu bu şekilde, sorulan kişinin duyduğu bu şekilde. Tamam mı? Yani onların zamanlarına
Evet.
kendi şeylerinde böyle ama birbirlerinin izlenimleri birbirinden farklı. Ne yapıyorsun genelde? İkisinin arasında şu kadarlık zaman farkı var diyorsun. Bu zaman farkını hem buna hem buna ekliyorsun her seferinde. Hem sorana hem de sorulana ekliyorsun.
Yani geç duyduğu için geç cevap veriyor. Ona da geç gidiyor.
Evet.
Bu kadar geç gidiyor. Arada bir
evet,
delay
her
var.
bip bu ona gönderiyor, ona gönderiyor. Birer bit gönderdiklerini düşün. Bu bit bana 5 saniye geç geldi. Onu aldı, proses etti. Bana bir bit daha gönderdi. Ne yaptı? 5 saniye onun gelmesini bekledi. 5 saniye şimdi ben onun gelmesini bekleyeceğim, değil mi?
Evet.
Dolayısıyla 5 saniyede oradan gecikme oldu. O zaman tekrar soru sorduğumda ben yine bunun aynısını bekleyeceğim.
Ama mesela bundan buna geç geliyor ya, bundan da buna geç geliyor gibi düşünmeli miyim?
Tabii ki ondan geç
Tamam.
geliyor. Çünkü o da onun bitmesini bekleyip tekrar soruyor. Ama biz bu tarafta olduğumuz için adam
direkt
sorusu
yolladık.
biter bitmez konuşmaya başlıyoruz ya. Sanıyoruz ki o bizi duyuyor ama o duymuyor bizi.
O zaman dediğiniz gibi durdurarak kaydedeyim. Ama o zaman mesela sizin videonuzda, sizin kaydınızda benim sesim olmasın mı?
Olmasın tabii.
Tamam.
İkisi ayrı ayrı yerlerdeler.
Tamam yani diğer karşıdaki
soru sorabilir miyim?
Neyle alakalı?
Neyle ilgili?
Ya ben biraz ara vereyim arkadaşlar ya. Ben sabahtan beri konuşuyorum. Durun ya biraz. Sonra mı? Ya ders arasında derste uyuyorsunuz. Ders arasında gelip bak. Ondan ders arasında.
İzafiyet teorisi.
Ben de güzel arıcılık yapacağım. 3 kere falan değişti inputu. Haberi baştan başlıyorum. Ve 100 tane veriyi kendim nasıl böyle çekeceğim? Kendi kendime konuşsam. 2 tarafta ben olsam. Arada çekmem. Ben 100 kişilerden bulayım.
Allah Allah.
Kendime konuşayım abi, ne olacak?
Konuş.
Onlara demoda göstereceğim video başkasıyla konuşurum. Diğer 99 tanesi kendimle konuşurum.
Ödevde hoca heceleyin demiş bütün
Evet,
kelimeleri.
heceleri ayırın demiş.
Kökünü ayıracak mıyız kökünü de?
Kök gibi değil.
Ya bütün her şeyi mesela kitapları dedi. Kitapları komple ayırdım hecelerine.
Kitapla.
Okey, tamam. Onu soruyorum.
Kitapla köke bakmayacağız. Ama en dokuzmuş ödem olduğunu düşünmüşüm.
Benim hayatımda sıkıntı yok.
Neyse.
Ödev hiç başladın mı?
Baktım.
Valla bugün bitirmeye çalışıyorum.
Ama heceler ayıracağız.
Heceleri ayırdım.
Tamam. Ama temizleyeceğim önce. Yani her şey küçük harf olacak.
Tamam, onları ben yapacağım.
Sonra heceler ayırdık.
Heceleri ayırdım, engramları çıkardım. Ama hocanın dediği işte,
Marco assumption'a göre.
yani işte neydi bu Turing bir şey. Onları ben yapmam. Onları yaptıktan sonra aslında şey yaptım. İşte neydi 3 gramla 3'ünü ürettim. Saçmalıyor yani.
Bir de hece ya kelime
Evet,
de değil.
aynen.
Kelime olsa zaten neyse. Marco assumption. Text yine fonlayız.
Hı hı. Oluyor.
Hayır, %5'e 95 ayıracağız.
Ha, training test.
Bir de çok zero olacak demiştim. Ben 75 demiş.
Ne olacak?
Zero, sıfır çok oldu demiş.
Nasıl çok olabilir? Sıfır mı yapacağız?
İşte.
Neydi? Ha. Ben de tam mantıklı yapmadım. Şey, içinde yaptığım şeyde. Zaten şey sana genel T'nin en kırılma bir şeyi var. O zaman
Hoca kızıyor Emre, az önce birisine kızdı.
ne?
Hoca az önce birisine kızdı. Yani
Anlamadım.
bir tane kapat diye.
Şu an iletişim haldeyiz. Yapacak bir şey yok.
Var kızlar haberin olsun.
Nereden aldın? Ben de siyahını almıştım.
En dışında şey yok.
Kulağından aldım.
İlkini aldım.
Sıcak bir içi bu var. Senin gidişini şey, biz alıp monta düşmüştük efendim bir kere. Aldığı gün.
Benim yapasım yok.
Arkadaşım ya.
Şüpheler gibi nasıl İyi hocalar ki adını bu kare. Ama ne diyeceğim?
Anlıyorlar onu.
Diğer
Sanki bu da yazmış.
bir dakika sağdan da var. Sulacağı da var. Şeyden de var. Aslında böyle beraber bir ürettik. Çünkü şu öğrenim daha nasıl?
Hafta sonu çok geleceğim.
Ne kadar var şu an.
Ondan sonra
Buradaki kaldı.
Gerçekten çok iyi.
Gerçekten.
Ama gerçekten
diğer geliştirmeyi açıklayayım. Daha işte yapanlar olduğu için. O kısımları daha yapanlar.
Evet, evet. Bir tık
Hemen oldu tam.
falan yoktu. Her şey aynı yerde. Aslında varmış.
O yoksa ben yapamam.
Aynen. Sen yok ama. İşte onu ayarlayabiliriz. Kaçış yapacaklar.
Bir buçuk saat kaç kişi var?
Başka bir tuş var ya.
Kaç tane şey var daha?
Bulamıyorum hiçbir şey. Ya benim 8 GB'den 156 GB'den çalışıyordu. Yani bir yavaş geliyor bana. Şeyleri özellikle Ubuntu'dayken. Ben Ubuntu'dayken aynen. Bunu açamıyordum yani. Böyle
Windows'a benim Windows'u sileceğim.
ama bundan sonra benim çok yükselmeye çalıştım. Bakalım. Ama daha kötüsü şey yok. Ne diyorum? Belki şey kurduğum için yok. Bir şey olacak falan böyle çantama koymadan önce bir de buna koyuyorum.
Ben de öyle yapardım değil mi?
Çizgileri sonra
Birisini öldürmek hiçbir şey
Masaya koymadan önce masayı falan.
Ama en azından okudum. Gelirken o da bugün.
İlk üç şeyini. Neler yapacağım? İlk üç şeyini. Ben bir
İlk yapmamız lazım.
Ama sen ne beklemiş oldun? Ben seni
tamam.
Benim parçalarım neyse en azından bunu yapamazsan diğer işleri
her şey insanlara. Söyleyeceğim
Ya da böyle şey.
Ben oraya katacağım.
Sadece
Yani katacağım. Çok korkunç bir geçiş olursa kafaya falan belki belki gel. Bunun sesi gitmez. Başkası dışımız olabilir.
Yani birbirine karşılaştık şu an. İki video var. Ama
Şey gibi düşün. Evde güzel bir video var ya konuşuyorlar. Haber İkisini ayrı ayrı almış. O yüzden birbirlerini seslediyor. Ama birlikte sunduğunda farklı oluyor. Ama o zaman böyle boşluk. Onun içinde boşluklar çakıştırıyor.
şey yapmam lazım. Yani diğer ikinci videonun konuşmaya başladığı anı alacaksın. Mesela bu bittikten sonra, bunun konuşması bittikten sonra bunun konuşmaya başladığı anı alacaksın. Eğer video ayrıysa oradaki dileği kaybetmek.
Kırmızı konuşuyor. Beklemek için. Kırmızı çıkması sessiz yani.
Tamam, evet bitti.
O da duymayı bekliyor. Burası sessiz aslında. Kıyıyor. Şimdi sessiz kalma karşılaştırıyor. Oraya bak.
Mesela şu dükkan konuşuyordu ya. Şu o adamın konuşması bittikten sonra o zaman
Ama şey yani kırmızıda mavi sesler
artık oluyor mu sesli var? Şeyler var işte. Watt diye bir şey var. Değmiş. Ben başlama direkt şey yapabiliyorsun. Adam sesini veriyorsun. Ne zaman sanmış, ne zaman sanmış, tek veriyor. Kaç geçti süresi ama orada bütün ses böyle ben geçti iyi olsun hiç
ahşap olduğu için sanırım barbarlarıyla yapmışlar. Çok kolay bir şey.
bundan o sahneden çıkarmış. Şey falan anlıyor yani. Anlıyor müzikten şey yapıyor.
Yakın arkadaşlar bir şeyler yapmak arkadaşlarım için biliyorum. Hani başka olmadığı birisiyle evle alakalı onlar ne bakmış diye
Okay, back to our slides. Again, regularization is something that we used to correct or at least lighten the effects of problems of gradient descent. We say that gradient descent doesn't find the optimal point all the time. In fact, never finds it in very large spaces, but it helps a lot by regularizing your solutions. Okay, so this is a regularization approach. Good. What? Yes.
Şu çizgide yatmasını biliyorsun değil mi?
Okay, so regularization says, okay, one thing with the machine learning models, okay, it is not that difficult to model your training data. Okay, you get a very nice. Okay, if I do this, if I increase the number of hidden layers, and for each hidden layer I have lots of neurons and no noise at all, and try to model it, it will find a way to model all of your data. Let me make it a little bit, yeah, okay, do it again. It will find a model your data somehow, and it will sometimes make your training loss near zero, okay? But that doesn't mean that your model will work very well in the real life, okay? In real life, it may not work at all. That's because I have too powerful model. It can explain your data very well, training data. But when the time comes to running it in the real world, it may not work that well. Okay, so regularization kind of addresses this problem to some extent. It is not going to solve everything, but it's going to address problem to some extent. Another approach of regularization is dropout. Dropout is very interesting actually. Says that, okay, from time to time ignore some of your neurons. Okay, for example, if I am doing this, ignore this neuron, or this neuron, and this neuron, etc. That's one of the regularization techniques. It might work. What happened here? Oh, it is, well, going crazy around that. Okay, anyway, watching this, like it's like fun to me at least. I don't want to do that. Okay, so dropouts is one regularization technique people use. Nowadays it is not being used much, but it used to be very big in 2015s, around 2015s. I am going to skip this one.
It's still useful, sir.
Dropout?
Yes.
Some people say that we should never use it.
Why?
Because the numbers are coming back better without the dropout for some networks. Okay, especially newer types of networks, they say that no, let's not use it. Okay. The thing is this: if I have a network like this, output of one network is output of one neuron is being fed to other neurons, and they are doing the same thing over and over again. If I do this, okay, 1, 2, 3, 1, 2, and 1. Remember what I did? It was, okay, W1, W2, and W3. The same thing is here too, and there too. If my input X, Y, Z is multiplied by, I multiply X with W1 plus Y with W2 plus Z with W3, okay? And if I multiply the result of this one with W4, okay? And if I multiply the result of this one with W5, doesn't matter if I have a single layer of networks or more than one layer of networks. Why? Because this parameter here is the multiplication of this one, and this one. Then I would multiply these two with this one. That would be my second parameter and third parameter. What I am saying is that if you keep doing this, using more than one layer is not going to work for you. So what you're going to do is, okay, after you multiply X with W1, Y with W2, Z with W3, you need to feed this data through a nonlinear function f. Okay, this nonlinear function f prevents that kind of thing from happening, and that f is usually, you kind of know this, okay, logistic regression stuff. So we call this logistic regression, okay, logistic function. Why? Because Whatever you put in a z, it maps everything between 0 to 1. Logical value 0 to 1. Okay, and this one is going to be t minus 1 to 1. This one is going to be again, okay, minus 1 to 1. And nice things about these are continuous functions. This one is not a continuous function because you see this, there are discontinuities in there, okay? They are not differentiable at those points, but we ignore it. We take the derivative of it at those points anyway, and it works, okay? These are some non-linearities. Without the non-linearities, more than one layer of network doesn't mean anything, okay? We like linear stuff because we have lots of good techniques for the linear stuff, but linear stuff doesn't help us if we have more than one layer. We need to add non-linearities. We need to add non-linearities. Nowadays we don't use any of those, but we use this one. I guess this is the non-linear function that is the most closest to the linear functions. It's just two lines, right? It is max, given the z value, you choose the maximum of z or 0, okay? So it is this very simple nonlinear function that's called the rectified linear unit, okay? And this is called Leaky rectified linear unit. This is switch, okay? So people come up with these kind of functions, but this one works very well. Again, the problem with this one is it is not, you cannot take the derivative of it around 0, right? Derivative of it around 0. That's one of the problems with this function. If we ignore that one, well, as engineers, we are not perfect scientists, right? As engineers, we can ignore that kind of stuff. You know the engineer's prime numbers? Prime numbers for an engineer. So an engineer defines the prime numbers as the odd numbers. So he says that my prime numbers are 1, 3, 5, 7, 9, 11, 13, 15, and 17, etc. These are my prime numbers, okay? Is 1 a prime number? And nothing else is a prime number, okay? So these are the prime numbers. Is 1 a prime number? Yeah, it is a prime number. It is divided by 1 and by itself only, and nothing else. Is 2 a prime number? No, because it's not an odd number, right? It is a number. I made a mistake there, okay? So it's a modeling error. Is 3 a prime number? Yeah, it is, because it's odd. How about 4? Is 4 a prime number? No, it's okay. 5? Yes. So this one is plus, right? This one is okay. This one is not okay. This one is okay. This one is okay. 4 is not again. This one is okay too. And this one is not okay again. It's an experimental error or modeling error, etc. Did I miss anything? So 10 and 11, this one is okay too. As you see, I made only 2 mistakes here. And this one is okay too. This one is 15, is not okay, modeling error. And after that, this one is okay. After that, the number of errors is going to increase, but after that, the numbers are so big that they are not meaningful in real life. Okay? That's how I explain it. So, as an engineer, I found such a solution. It's good enough for me. Okay, so usually mathematicians make fun of engineers by giving this example, but as an engineer, if I think that I can take the derivative around 0, by knowing that there is a problem there, I just took it. I just took the derivative. What's the problem here? Okay, we don't know the derivative of this. The slope could be this, or slope could be this, or slope could be this, and etc. There are a million different slopes in there, right? It's not defined. The derivative is not defined. But assume that I took it, okay, and I run my numerical differentiation methods around that too, and look at the results, and the results came back very nicely. So I think that I'm ignoring that problem and I'm taking a derivative around that one. It works. That's what I'm saying. Mathematically it is wrong, theory-wise it's wrong, but practically it's like my prime numbers, engineer's prime numbers approach. Okay, so this one we are going to use. For the parameter initialization, remember how I initialized this one? Remember how it's still working? It's going crazy around there.
I guess it stops when you change the page.
What?
It stops when you change the page.
Really? So let's, so 140, 150. Wait. Yeah, you're right. It's not, but if I do like that, still works.
This may also overheat your laptop, sir.
What?
This may overheat your laptop.
I don't care, just, yeah,
Continues to run.
yeah. Right. I think it is overheating because I am charging it. I am recording this session too. Anyways, okay. Let's stop it. Okay, so how did I initialize this one at the beginning? Let's stop it and start from the beginning. Initializations are, see, these are the initial numbers. Random numbers around 0. If you see them, these are just numbers around 0. So usually I take them from a uniform, not uniform, but Gaussian distribution around 0. Don't make them symmetric, don't make them all zeros, don't make them the same numbers. That's what you do. There are initialization techniques for this one. And this one, Xavier, initialization has variance inversely proportional to fun-in. Fun-in is how many inputs do I have in, okay? If you have so many, then you increase this number, and that's my variances. And I think this one, initialization, where is, do I have initialization? Learning rate, activation, regularization rate. Oh, see, I did not do the regularization rate previously. I wasn't doing any regularization at all. Remember that, remember this parameter, lambda, that's the regularization rate, okay? I forgot to make the regularization there. That's the regularization rate, and the alpha is the learning rate. Remember the alpha, learning rate, this one, where is it? Yeah, this is the learning rate. That's what it is. Learning rate is this one, regularization rate is this one. Just do it now and see all these numbers are not getting larger or smaller. It is behaving more stationary right now. Okay, so all the numbers are initialized close to 0, and network initialization is something that we need to be careful about. Let's make this a little bit smaller and let's see what happens in a few minutes. Okay, so that's the gradient descent. Oh, not that one, this one. Regularization, talked about it. Nonlinearities, parameter initialization, we talked about it. Optimizers, as we said before, we are using the stochastic gradient descent, okay? But it has different versions of it. Adaptive gradient descent, RMS prop, ADAM, these are all some variations of the stochastic gradient descent. This adaptive gradient is change your learning rate, okay, depending on your progress. So our learning rate is not the same all the time, but I'm not going to go into the details of those. Learning rates we talked about, again, some of the stuff. In this case, our learning rate is fixed, 0.03, but sometimes you like to make it a little bit Make it start learning fast, and then learn a little bit slower. That works the best. This guy is not doing anything. Regularization is too much. Make the regularization a little bit less severe. Okay. No. I'm going to stop this because it's taking too much time of mine. Okay, so that's the learning rate. Okay, let's go back to our language modeling thing. We already know this much. Okay, we know that given these first T words of a sentence, okay, try to estimate the next word in my sentence. Okay, so the students open their, is it books or laptops or exams and minds? Okay, choose the correct one. According to what? According to your language model. So we did this before, statistical language modeling. We did this using the n-grams, 1 gram, 2 gram, 3 gram, whatever. And your homework is about using syllable grams of Turkish, right? Somebody had a question about homework. Did you have a question?
Yeah. Should we syllabalize each word, root of the word, or?
True, yeah, but it is difficult to get the root of the word because in Turkish sometimes the inflectional words, inflectional suffixes, right? They are mixed up with the root itself. So don't try to get the root itself correctly. So treat a word like a regular word. Don't care about your suffixes and the root. Separate them into components, 2-3 letter components, like defined in Turkish. Then run rest of your algorithm. Okay, that will be easier. So you are going to do this n-gram thing in your homeworks. Okay, so we know how to do that modeling. But the problem with the n-grams is what? What is the problem with the n-gram modeling of a language?
Some words for n-grams are too infrequent, too small.
Yeah, that's why we need to use smoothing and etc. And if you like to do it more than 5 grams, then you are in trouble. Only Google can do 5 grams, right? And the other thing is for Turkish, each word has like 5,000 different forms. How are you going to do the n-grams for Turkish? It's a difficult thing. What is the root of each word? To find the root of each word, you need to do the morphological analysis. But morphological analysis is something ambiguous, very, very ambiguous, especially for common words. That's going to be a problem. Even if you do it right, you need lots of memory, right? That's what you do. So for those kind of reasons, we don't want to do n-gram, statistical n-gram based modeling. That's why I didn't ask you to do the n-grams based on the words. That would be a big thing, very, very big thing for you. That's why I asked you to do syllable based n-grams. How many syllables do we have in Turkish? Usually syllables are like a vowel and a consonant vowel, right? Consonant vowel consonant, right? Is that
Vowel only.
vowel what? Vowel only? So how many vowels are there? 8 times. So this is 8 times how many consonants? 30. How many letters in Turkish? 20.
21.
Okay, 21 here. So 8 times 21 times 2 is this one, right? So this is around 16 times 21. Okay, but these both. How about this one? 21 times 16 times 21 and no, 21 times 8 times. 8 times, and this one is just 8. So I am talking about like how many? 20 times 20 is like 4,000, right?
We also have C4.
What?
C4, for example.
I guess I'm going to ignore that one because the number of I cannot do that kind of because those kind of syllables are very rare. If you add them up, I think it is not more than 50, 20, right? I can separate them in a different way. These are more common. So 400 this one, right? And this one is 400 times 10, 4,000. So I'm talking about maybe at most 5,000. So to calculate a 2 gram of syllables, it's just 5,000 by 5,000 matrix. If it is trigram, it is 5,000 by 5,000. So it is not, and it's not a very big thing, okay? It's not a very thing. So you might say, why don't we do the letter-based n-grams? We can do that too, but that will be too weak model. It's not that wouldn't be a very strong model. Okay. So again, instead of using n-grams, we like to use neural language modeling. We already did that using the Markov assumption and the chain rule. Well, we use the language model everywhere, like this one. What is the weather? How is the weather? Where is the something, etc. Okay? What is the meaning of life? Yeah, here it is. So did you try this GP3 chatbot?
Yes.
It's good, right?
Yes.
Very
good.
Yeah. I wonder if I can use it to grade the students' answers in exams, because they are telling me that everybody is doing their homeworks by using that one.
But it usually gives incomplete or wrong answers.
Well, I mean, it doesn't have a mind, right? It's just statistically whatever maximizes the answer, it just gives you that one. Usually grammatically correct results and usually politically correct results are most of the time how we answer stuff, right? You know Eliza, right? You know Eliza? Eliza, the first chatbot, people had written it in like 1950s. All it does is just, you ask a question and the system asks that question back to you again in a few more minutes, and when people heard about it, they thought that in a few years chatbots will be all over the world, but that didn't happen yet. Okay, so n-gram models, we already talked about it. Okay, n-gram models are easy to calculate, but you need lots of memory and lots of resources. Okay, we talked about those, but these are the problems with the n-gram. Sparsity problem. We need very large matrices, 40,000 by 40,000 by 40,000 matrix for a trigram model for Turkish, and 40,000 is not enough. As I said, it should be 40,000 by 5,000. So, and many of the elements of these matrices will be empty, so that will be sparsity problem. Okay, sparsity problem. Some of the things will not be observable. Okay, so partial solution is add small. Remember the advanced smoothing? It one says that advanced smoothing. Okay, and the sparsity problem again. What if students open there never occurred in the data? Okay, it never occurred. That doesn't mean that its probability is 0. Okay, so maybe we can do the back off. Instead of calculating trigram, calculate bigram. Okay, that's another kind of solution. Weak solution, but solution. We need lots of storage. Okay, those are the problems. So what can we do? And so this shows the sparsity problem. How can you say that? Okay, so we said that today and I am trying to guess the next word. Bank and company have the same probability. Italian and Emirate has the same probability. It says that it has sparsity problem. How can we say that? Why is it saying so?
Couldn't sort.
So why is this a sparsity problem? It looks like today the happened only maybe 10 times, right? Very little. So I need to assign these similar probabilities also. There is not enough granularity to differentiate between the possible solutions. Okay? Okay, so I am going to move off this one. Well, one nice thing about this language model is we can produce sentences like this, right? Today the price, what is the most possible word out of the price is, it looks like of. Today the price of, after the of, what is it? Gold. And I can continue that way, okay? And this is some language generated by engrams. Today the price of gold per ton, while production of shoe lasts and shoe industry, the bank intervened just after it considered and rejected not coherent, just nonsense stuff, but grammatically looks okay. Okay, we know that. So we are not going to do language modeling using engrams, but we are going to do, okay, neural language modeling using neural network, of course. Previously we did this, remember, 200-dimensional vector, and we fed it through two-layered neural network, and this one said that Paris is a location. Okay, that's what we did. So this is named entity recognition problem solution using the neural network. We are going to use the same neural network to model the language. How we are going to do it? We are going to take these words. The students open there, and we like our network to guess this word. So this is what we are going to do. This one, okay, this one is a 40,000 dimensional binary vector. Okay, it's a one-hot vector. When I input this one, the students open there, and I like this network to estimate what is the next word. And it's going to say that, okay, I am estimating that the books has a probability of this much, laptops is this much, and this one is this much. Okay, that's what we are going to do. A fixed window neural network, neural language model. You give these 4 words, and it will give you probabilities of the possible words. Nice, right? So what are we solving here? If it works, what are we solving here? Remember the problems with the engrams? It's unbelievable what a simple cable can do. Just I thought that this projector is going bad. So what are we solving here? Space problem. Remember space problem? We need trigram space. Okay, if I have 40,000 words in my dictionary, I need, for the trigrams, I need 40,000 by 40,000 by 40,000 matrix space, right? That's a loss of memory. In this case, the number of parameters are, how many parameters do I need? If the input is 200 dimensional, if I have only 16 neurons in there, okay, 200 times 16 plus some values, so we are talking about 2,000, 3,000 parameters. That's it. Very, very compact. Can I learn such a complicated thing using just 2,000, 3,000 numbers? Well, if it is not enough, just add a few hidden layers, right? Add more neurons, and then you are on your way to achieve a language model. Okay? The nice thing is, this will work very, very well for cases where you didn't see any examples of. Maybe you have never heard the students open their word grouping together, but this one is going to suggest you something, and most of the time it's going to be a good suggestion. Okay, the smoothing problem, we won't have any of that smoothing problem. Okay. I love you guys when you the back side of the engine. You guys are unique guys. Okay. In the front row, I have only two people, one there, and back side of the class is all crowded up. Okay, so those are the big advantages, and we are going to use those advantages. Okay, the only thing might be maybe we need more complex network than this, but it will not be as expensive as trigram or 4-gram or 5-gram statistical language models, and this will be more generalizable. Okay, so that's it. No sparsity problem. Just a minute. No, you don't need to store all observed n-grams. So sparsity problem goes away. If I didn't see something before, what am I going to do? Okay, that's one thing. It will go away, and I don't have to store all that thing. Okay, yes.
Do they output one-hot vectors or word vectors?
Well, it would be more logical to output a word vector. Yeah, that's true. But this one didn't talk. Well, I mean, the slide, the source that I have stolen these slides from, the guy didn't talk about the word vectors yet, I guess. That's why.
But input seems to be a word vector.
Yeah, well, it didn't talk about the word vectors yet. But yeah, I can output a word vector. In that case, instead of outputting a 40,000 dimensional binary vector, you are going to output a 200 dimensional vector, yes. That's true. Okay, but there are problems. Problems is this. Remember when we say what is the probability of having a sentence of length 10 or 20, our statistical language model can assign probabilities to those kind of sentences, right? Remember the chain rule and the Markov assumption? Even though I am using 2 grams or 3 grams or 4 grams, I can assign probabilities to sentences of arbitrary length because of the chain rule. I don't have that flexibility in here. I can only tell you the word right after these 4 words, okay? So I cannot make this work for arbitrarily long sentences. That's one thing, okay? You might say that, why don't we add more words here, okay? Instead of inputting 4 words, how about 5 or 6 or 7? Well, that will make your network more complicated, and still your size is fixed. If I make this number of words input as 10, and if I input only 2 words, what happens to the rest of the inputs? Am I going to feed null characters or null words or that kind of stuff? That becomes a problem, okay? That becomes a problem. So we need to find some solution for those, okay? Solution for those, and we are going to find it, okay? The solution is recurrent neural network. That's what we are going to do. The core idea is apply same weights repeatedly over and over again. So remember, if I input this, it's going to give me an output, right? Next time I shift my words, okay, to the left and give another words just after this one and ask the results back. So repeatedly, the same weights over and over again is applied. Okay? So let's say I input a word and it gave me 1 word back. I input another word, it gave another word back, but the internal hidden state, I am including that internal hidden state in my new calculation too. And I am doing the same thing too and same thing too. So that way I can add as many words as I can, and every time I do that, it's going to give me a new result. Okay, it's going to give me a new result. So I can run any length of sentences through my network, and it's going to work. That's called recurrent neural network. They are very old, from 1990s. Okay, way long before the deep learning became very popular. They have invented this, and it works incredibly well with a bunch of parameters, hundreds of parameters, maybe thousands of parameters. That will be enough to model a language, and better than, most of the time, better than the n-gram-based models. Neural language models, they started working on n-gram-based models in 1950s. Up until 2010s, they were the best, okay, to make a model of a language. They are very, very primitive models. Remember, I told you about the n-gram-based models in just 1 or 2 hours. That was it, okay? That was it. They are very, very primitive, but they work very efficiently. So people have been using them for 50, 60 years. And nobody, no matter how complicated theory is, nobody was able to beat them until 2012 and 2015s, where the neural language modeling became more powerful than those. Nowadays, everybody is using neural language modeling. Okay, maybe in some cases a hybrid approach between the n-grams and the neural language modeling, but most of it are pure neural language modeling. Okay, so this is what we are doing. The students open their, is fed through my network, then students is fed through my network, but network remembers what it said before, and the new internal state of the network is calculated using my, let's look at it. The hidden state of my network is some weights, okay, multiplied by my previous internal representation plus my new input times the weights for the new input plus some bias. Okay, so that's what I do. These are my weights and these are my weights. So my internal state is not dependent on my input only. It is dependent on what I said before, what I thought before, and doing the same thing and same thing. Remember, the blue ones and the green ones are the same. Okay, these are all the same weights, and these are all the same weights. I'm not changing my weights from run to run. So very efficient. Keep using the same weights over and over again. And at the end, I am getting this one, whatever it is, and I feed another one, I get another one, another one. So there is no limit to this. There is no limit to this. I can handle arbitrary length sentences using this simple RNN method. Okay, I can process any length input, computation for step t, use information from many steps back. Model size doesn't increase for longer input. That's important. Whatever the input is, okay, it's just this and this. That's it. Okay, same way is applied on E every time step. So there is symmetry in how inputs are processed. It is not like I am not changing their order. Order is important too. Okay. Maybe you might say that it is a little bit slow. Why? Because to get to the final one, you need to feed all of them one by one, and you have to wait. Okay. That's maybe some of the disadvantages. Okay. Any questions? Did everybody sign the attendance sheet? Everybody signed it? Okay. So let's take some break. After the break, we will we will finish up at these arenas at least. Arkadaşlar arkada kötü uyuyorsunuz ya. Gelin ön tarafa doğru biraz. Çok mu sıkıcı ya ders? Ha? Çok mu sıkıcı?
Ben de oraya kesildim. Oradan sonra çok toparlayamadım. Çok çıkıyoruz gibi oluyor.
Her bilgi sorunlarım var. Şimdi sabah başlıyorsun ya çalışmaya. Sen işliyor. Okula geliyorum. Bozuluyor mesela. Sıfırdan başlıyor. Yani fazlası olduğu için. O sorun olabilir mi?
Buradaki benim hata çok kötü.
Hayır, bilmiyorum ya. Bak şimdi. Nasıl çalışıyor musun sen? Eğer bir saatten falan fazla hareket etmezsen ilk bağlantı kapatıyor. Bağlantı kapatınca da tekrar bağlaman gerekiyor.
Evet.
Tamam. İşte tekrar 9 saatten başlıyor. Sen mi sordun? Yani gün içinde 9 saati tek seferde tamamlamak mı gerekiyor? Yoksa toplam 9 saat olması gerekiyor.
Toplam 9 saat olması gerekiyor öyle şey. Mesela çalışmaya şey olmuyor.
Epey sonra 4 kullanmış.
O yüzden mi?
Benim şu an sıfırlandı mesela. Salta. Tamam. Onu da çok zor.
Ben bir sorayım.
Böyle okula giderken, gelirken de arada gidiyorum, gelirken sadece baştan başlıyorum. Oturuyor musun? Çıkalım. Çıkalım da.
Ben şok. Eğer öyleyse.
Değil mi? Hiç çalışmadım.
Evet abi ben.
Şey yaptığımda telefon kırdık. Hani evet, açık olduğu için gözüküyor. Düzeltmişler. Aynı şeyler aynı.
Çok saçma. Öyle şeyler.
I think they also
Böyle bir şey düşünüyorum. Sen de gösterin. Şey yapmışsın çok iyi. Bütün koruyucu dışında kullanmalısın. Sağlığınız böyle bir şeyler falan. Yapılmış bir şey. Sadece şunu çalıştırmalısın.
şey dosya alıp read.
Onu da yapabiliyorsun. Mesela paylaşmıştım ya. Yapmıştım. Klasik dosyayı yazabilirsin. O yüzden o yüzden senin diyecektim işte.
İnternet tarafından yani kendi kodunu çalıştırmak için falan çok iyi. İşte bunlar nasıl zamanlar kullanacaklar. Bir şey indirmek istedim. Onu indirmek için insanın en eğlenceli uyku olması. Ya fail videosu çekiyorum. Çizmek kolay değil mi? Yani yemek kullanmak mı?
Sen yanlış yerde mi oturuyorsun? Hayır, bir önceki ders orada Sibel oturuyordu.
Ben arada geldim.
Sibel nereye gitti? Ne yaptın Sibel'e? Sibel oraya mı gitti? Tamam. Arkadaki arkadaşları da küstürdüm, gittiler ya. Sürekli onlara bakarak ders anlatınca. Şimdi yeniden yoklama mı alsam hocam? Okay, so that's the RNNs. RNNs are, as I said, in many respects they are better than n-gram-based language models. But of course, as always, there are problems with it. They are slow. Why? What do I mean by slow? You need to wait. You need to wait until the whole computation is done. You need to give these. Okay, you don't give these four in parallel, right? You give this one, you calculate this one, and you give this one, you calculate this one, and this one, and this one. Even if you have a very massive parallel computer, you have to wait until you reach the end. So that's why they are slow. You cannot take advantage of your GPU stuff, etc. Okay. And the other thing is this. What? I'm going to skip this one. Okay. Remember how we did the negative log of the scoring functions and we add them up? This is what you do. When you say this is how we train it. When I give this the input, I am expecting to get a students. Okay. For the label is students. For the students, the label is opened. For the students open, the label is there. Okay. So that's how you do the loss. So loss is always you are adding it up. And when you do the parameter optimization, okay, when you do the parameter optimization, you try to minimize this loss and this loss and this loss and all the addition of the losses. I think I'm going to go further. And yeah, this one. I am going to minimize this loss. Okay. So this loss, the parameters are, it looks like it's a very complicated network, but it is not. Because my parameters are simply this one and this one, that's it. Because rest of them are the same. So the number of parameters is not that much. But when you do the loss, okay, you need to take this loss and you need to go back to all these paths. Okay. So you are going through the same parameters many times. That's one thing. The other thing is that, see this one is very long. It is going through many paths. Okay. And it is long. That means what? That means I keep, remember, to take the derivative of this loss with respect to the parameters. Okay. I need to follow this path. And on that path, there are many differentiations happening. There are many derivatives are happening because of the chain rule. But for that one, I think I need to go back to this slide set. It looks like I cannot. Not that one. Not that one. Maybe this one, yeah. Okay. Okay. So we already know this stuff. Just a minute, okay. You know how to take the gradient of a function with respect to x, right? So we already know this from high school. Okay. But if the function is a multidimensional function, like our functions, then you don't have a single scalar number. You have a vector of derivatives. So take the derivative of this f with respect to x1, x2, x3. So you get a vector back. Okay. So because this is an n-dimensional function, your derivative with respect to all of these dimensions is going to return n-dimensional derivative result. So your direction of gradient descent will be n-dimensional. That's kind of expected. And If you have a function of functions like this one, then you have many lines of this derivative. This is called Jacobian matrix, function of functions. In multi-layered neural networks, we have functions of functions because each neuron is like a function, and the result of those neurons will be fed to other neurons, and that will be functions of functions. This is how we do it, and we have the chain rule. Okay, if we have this one, z is equal to 3y, y is equal to x squared. Okay, if I take the derivative of z with respect to x, well, you don't see any x's in here, but y is dependent on x. So this is what you do. Derivative of z with respect to y times derivative of y with respect to x. This is how they teach you, right? For the calculus class, and this will be the result. Okay. In our networks, remember, I feed. Okay, this is my input. Multiply this input with w's, add some other constants, and feed it through this function f, and you get your result back. So if I like to take the derivative of this function with respect to x, so you take the derivative of this h with respect to z and derivative of the z with respect to x. Okay, so if I put more layers between this input to the final one, so you need to do this derivative operation many times, and you will end up multiplying all of them together. Okay, you need to end up multiplying all of them together. And just to give you an example, no, I am not going to give you an example on this one. So the problem in this case is this. Okay, since I am going back through many layers, okay, every time I go through, when I take the derivative of this loss function, derivative of this result with respect to these parameters, this result with respect to these parameters, this result of these parameters, I keep multiplying them over and over and over again. If those derivatives are very small values, if you multiply many small values together, they will get close to zero, and that will produce numbers very close to zero. That will be a problem for our computational models. Why? Because we cannot represent very small numbers near zero. It will cause an underflow, right? Not overflow, but underflow. And even if it doesn't cause any underflow, derivatives will get very small. If they are small, remember the slope that I showed you? Remember that one? I showed you an example like this. I said that if I take the derivative of it, very nice steep slope in here. I can't make it a little bit like that. Okay. Erase it and draw it again. So at this point, I have a slope like that. Very nice steep slope. Very fast convergence in this case. But if I am around here, slope is very slight, and it's not moving me very much. Okay. So if you multiply many derivatives together, your slope will be almost horizontal. You won't be moving towards your solution, towards your optimal results. That's what's happening with this training of RNN language models. You are going through many layers, okay? Although they are using exactly the same parameter set, still you are going through many layers, and multiplying all those chain rule derivatives will give you very small values. That's called vanishing gradients. Vanishing gradients. Vanishing gradients. Okay? Vanishing gradient means that your derivatives are getting small and your gradient descent is not moving as fast as you like. It will be blocked, and soon it will be overwhelmed by the error and the noise in your system. You are not going to go anywhere. So training such systems is difficult, and we need to find some solutions for it. Okay. Okay. So we talked about this, and back propagation for the RNNs is difficult. We talked about it. I'm going to skip these details. Back propagation is going to cause, okay, vanishing gradients, and okay. Remember our text generation stuff? We can do exactly the same thing. You just give your words. My favorite season is, it is supposed to produce something spring. Then I would put spring in and get another word, another word, another word. So that way RNNs would produce sentences. And this is a sentence that is, your RNN is trained using the Obama speeches. And this is something that the RNN produced. The United States will step up to the cost of new challenges of the American people that will share the fact that we created the problem. they were attacked, and so that they have to say that all the tasks of the final days of war, that I will not be able to get this done. It sounds funny, but this looks like Obama, right? Okay, it's better than what we had with the engrams, and this one is really a very small network compared to your engram approach. Okay, generating text with RNN language model. I think they trained this with the Harry Potter stuff.
ChatGPT could do better, I think. So.
Well, sure, yeah. Well, I mean, these are from 2015s, like 7 years ago. 7 years in deep learning world means it is centuries for other areas of science, right? Okay, but I mean, we don't know what's going on with GPT. Well, I know what's going on with GPT-3, but it's lots of data and processed together. All we are doing here is this, okay? That's it. I am giving you the whole detail. The whole detail is here. Gradient descent is 100-year-old method. Neural network is from 1950s. We know what was going on. So all the details are here, and from a simple thing like this, I can produce. Remember the theory I told you about. If we are going to do the NLP, we need to do the morphological analysis. After the morphological analysis, we do the syntax check. We do the part of speech tagging. After the part of speech tagging, we look at the ambiguities and etc. This guy says that, well, no, don't do any of those. This is just a statistics problem. All you do is just train a network like that. You don't need to know anything about the language grammar. You don't need to know anything about the morphology of the language. All you do is just learn a network like this, and it is going to produce your sentences. That's what we are saying. Okay, so I mean, I'm not saying that these sentences are perfect sentences. I'm saying that these sentences are produced by very simple networks. And I think I showed you this before. The unreasonable. Did I show you?
Yes.
The unreasonable effectiveness of mathematics and natural science is a classical paper by some guy. Okay, the guy is amazed by how the mathematics is solving many problems for the natural sciences. Okay, that's the paper. Eugene Wigner, whatever, physicist. Okay, then we have the unreasonable effectiveness of data. Okay, this one is by Norvik. What am I? Am I getting the mathematics again? Yeah. Okay. And then we have the unreasonable effectiveness of RNNs. Okay. And this one is by Karpati. Okay. I think he is with. I think he was with Stanford University, and later, I think he is with now some company, maybe with Tesla. Is it? I don't know where he is. Just could you look it up? He says that, but simple network like this, it can do many stuff, like the generation of the. By the way, this is a character level language model. Using even this one, produces lots of this. What Tesla? He's with Tesla, yeah. Because he worked. So what is he doing with Tesla? The NLP guy. He works on both vision and NLP. Okay, so read this one. See, this guy is producing some. This is a paper written by RNN, simple RNN, with a few thousand parameters. Since I don't know what it is talking about, I can assume that it is something meaningful. It's a mathematical theorem, I guess. Right? So these are question marks because it didn't get the label numbers right or the labels right. Okay. Other than that, everything is directly produced by that guy. And this is the Linux source code. It is producing some code, right? Syntax-wise, it is okay, but it won't compile. Why? Because I don't think that these mem total is a defined variable. It doesn't have the semantics right set in. Okay. So we looked at those. This is. I mean, some people mark this as they go all the way to unreasonableness. We don't understand why it's going on. This is fun. So they trained the network on color plates from the paint color catalogs of the paints, right? So they asked the RNN to produce some color names. So for that one, you know how they make up the color names? Gas the pink, power gray, navel tan, horrible gray. I don't know how they come up with the names of those car colors, for example. Okay, just fun. Okay, so as always, we do measure our language performance using the perplexity from the information theory. Okay, lower perplexity is better, remember that one. And these are as of 2017, 2018. These are some of the perplexity numbers of systems. Lower the better, right? So can I erase this? Yeah, I can erase it. Yeah, sure, yeah. So interpolated 5 gram. This is pure classical n-gram, okay? 2013. Perplexity is 67. Okay? Google model, 5 gram. You cannot do better than that. Okay? But if I do, how come, what? 9 gram? How come they can do 9 gram? What do they mean? Can anybody guess? They say that I am doing a 9 gram as the same guy. If Google can do 5 gram at most, how come this guy, which is from Google, can do 9 gram?
Maybe it is letter based.
Who is talking? Yeah.
Maybe it is about letters, not words.
No, it says words. This 5 gram, the meaning of this are the same. Look at this one, RNN 124, it is RNN of neuron size is 1024. Okay, but how about this 9 gram? They only they only use very common phrases up to 9 grams. They don't calculate everything, okay? They only calculate only frequently occurring 4 grams, 5 grams, 3 grams, and etc. They ignore less frequently occurring stuff. So maybe some 9 grams, the total number of 9 grams they have is maybe 100, a few hundred, maybe 1,000. The rest is handled by the RNN. So RNN is a very nice generalizable thing, okay? For the rare cases, it works. For the commonly occurring 9 grams, very robust statistics, okay? It is 9 grams, okay? So perplexity dropped a lot. Then RNN to 48 to K, blackout and sampling, and this one doesn't use any n-grams. Sparse non-negative matrix factorization, I don't know what that is. Then LSTM is a kind of version of RNNs. And this guy says that, I don't know who this guy is, JFP. Okay, he says that I can drop it down to 39. Very big difference between these two. I guess this one is from 2018s or 17. Okay? So we'll talk about this LSTM in a few minutes. Okay? So, of course, I mean, I'm not going to talk about language modeling. It is something that we use all the time. Almost all the NLP applications use it. Predictive typing. Now you know how that when I say bugünkü maçlar, when I say bugün, right? Bugünkü maçlar, bugün ne pişirsem, bugün emekli olsam, bugün nasıl yazılır? So you know how it works now, right? They feed this word to an RNN or LSTM, and they get the most probable the third one, okay? Bugün maç sonuçları. Bugün maçlar Süper Lig. In English it works better when you start who is Yusuf Sinan Akgül, right? So it is customizing for me. Who is domain? Who is Adar? Does anybody know? Andrew, I don't want to click on any of them. I don't want to. Does anybody know what that is? So how about this one? Where is my IP? Where is my phone? Where is my location? Where is Turkey? Where is my mind codes? Okay? So these are the most common questions, maybe coming from this university, maybe coming from me, maybe coming from people type like me. Okay? So you know what's happening with this, right?
As I know, this uses database also.
Without the database, no. It's coming from a network. They use a database to teach it, but it is directly. How else can you download that network, that database to your computer? Because it is running on my computer. Even if I am not connected.
It doesn't work if you're not connected.
Let's see. I am not connected now, right? So there is a network in there. So when I say, where is something? Where is my mind?
Use different words.
Okay, let me open a new thing. Okay, where is? Oh, it didn't do anything. But as far as I know, it downloads the parameters of the network on my computer and it runs it through that model. Okay, since it is not connected, it doesn't want to say anything updated, not updated. Okay. So it doesn't, of course database should be there, but it is using a network like that.
As I know, it makes correction, word correction.
Yeah.
But it uses a database. It queries against the database and picks the top records. And it also adds your location and other information.
Yeah. Well, it's a network. So if this guy lives in here, and his IP is coming from a university, and he asked me these kind of questions, so it's a typical network. It is not Rule-based system. Okay. So language modeling, we talked about it, and that was the language model, recurrent neural network. Of course, recurrent neural network doesn't mean that it's a language model. We can use the recurrent neural networks for doing many stuff. See, every time I feed something in, it gives me the determiner, adjective, noun, verb, and determiner noun. So I am using it for tagging. So this is called sequence-to-sequence neural network. Sequence-to-sequence. Sequence-to-sequence neural network. Okay? For each word, there is an output. But okay, tell me the problem with this approach. Compared to what we did before, tell me the problem.
Doesn't know the later words.
Yeah.
Doesn't know the sentence.
Okay, when I say the, it didn't see the rest of the sentence yet, right? I say the and it says the determiner, so it doesn't know the context, right? Because I am feeding starting from the left to right. Okay, when I say startlet, okay, the startlet, it says the and adjective. It doesn't know the rest of the sentence. How can you make this? Tag assignment then? So that's a problem. So what would be your solution? Run the same network or a different network from the other side. Start from the last word and go backwards. Well, in that case, it's not going to know when I say vase, okay? It doesn't know the beginning of the sentence. That's another problem. So the solution is, maybe I started looking at it early. Solution is, okay, I think I started talking about it early. Okay, solution is this. Solution is bidirectional LSTMs or bidirectional. Anyway, I'm not going to find it. Solution is this. Solution is, okay, run the network this way, run another network this way, get the results out, okay. I have two networks. Each one is telling me something. Get the results out, run another network on top of it. Okay, that's called bidirectional. Okay, so RNNs are not used only for language modeling. It is used for sequence tagging, like we did before, or sometimes they can be used for parsing too. Okay, and they can be used for sentiment assignment. Overall, I enjoyed the movie a lot. Okay, and this one is outputting a score. After reading the whole sentence, it is outputting a score. It's called sentiment classification. Okay, and RNNs can be used for question answering. Okay, I have lots of context about Beethoven. Okay, as the context, I have that information in a network, and I get this sentence. It is encoded, and I feed that two information into another network, and it's going to give me the answer German. What nationality was Beethoven? It is German, right? We can use RNNs to generate text from sound, speech to text, from audio to text. It works very well. And I guess that's it for now. Okay, these are the plain vanilla RNNs that we talk about. And now we are going to look at different versions of the RNNs, like the GRUs and LSTMs and the multi-layer LSTMs. This is nice. This is really, yeah, different flavors of it. But this one and this one taste much better than RNNs. And these are really multi-layered. Okay. And what is this? What? Aren't these? Ya bunlar tuzlu değil mi ya? Ya bu Amerikanlar kadar neyse söylemeyeyim şimdi. Okay. Onlar da aynısını bize söylüyor. Sabah kahvaltısında turşu yenir mi diyor ya. Ne diyorsun diyor. Turşu yiyorsun. Zeytin yemiyor musunuz diyor. Zeytin turşudur diyor. Doğru söylüyor diyor adam ya. O da aynısını bize söylüyor. Turşu yenir mi diyor kahvaltıda diyor.
Ciğer yiyoruz hocam.
Ondan bahsetmedi. İşkembe yiyorsun sen. Ama yine de yani dondurmaya ne tuzlu şey katıyorsun ya. Okay, so let's start looking at those fancy RNNs. At least I can make a small introduction to it. Okay, the slides that I have stolen these slides from Stanford University's NLP lectures. I think I have stolen them last year, I guess. Okay, so Manning is the guy who wrote these slides, and I think he had lots of guest lectures. Okay, so we are going to look at this vanishing gradient problem. I already talked about it. RNNs has this serious problem of vanishing gradient problem. But before going into these LSTMs and the GRUs, because I don't have much time, I have only 5 or 8 minutes. I need to start from the end of it because I don't think that I will be able to tell you what LSTM is in that time period. Next time I'm going to tell you what that is. Let me do this then. Okay, bidirectional LSTMs. So that's the problem, remember? So, forward LSTM, the movie was terribly exciting. Okay. This is the forward way and it's going to produce something. This is the backward way. It is producing another thing. If I combine these two together, okay, concatenated hidden states, and if I feed that information to another network, that network will give me the final verdict on this one in terms of sentiment. These are called bidirectional RNNs. Okay, so and forward RNN and backward RNN, this is the concatenated hidden state, and from this hidden state I can produce my final result using another network. Okay, what else? Simplified diagram, we talked about this. Multi-layer RNNs are these, okay? This is my first layer of RNN. I feed my data from left to right, okay? I don't produce anything out of these, but the output of the first layer of RNN becomes the input to another layer of RNN, okay? And the output of the second layer becomes the input to the third layer. Usually we don't do more than 3 or 4 layers, okay, for the RNNs, and these are called multi-layer RNNs. If you connect together these 3 layers of RNN with the bidirectional stuff, so it becomes multi-layer bidirectional RNNs, okay. And I guess that will be it. I think I will stop at this point, and next week I am going to start talking about these LSTMs, and then I kept talking about this neural language. I kept talking about language translation, okay, machine translation as an ultimate NLP application. Finally, it is time to talk about neural machine translation. How did the people do it before, and now how we are doing it? And I will talk about the language models, of course. Okay. One of the earliest parallel corpora is between the Hittites and the Egyptians when they started the war in around Syria or something like that. Their agreements, they were written in 2-3 languages. Okay. And the Rosetta Stone is not that one, but it's one of the earliest ones. And usually people did this kind of stuff. Anybody knows German? Yeah, Morgan is not morning. Tomorrow.
Morning ama tomorrow olarak da kullanılabiliyor.
Really? Yeah, okay. So I fliege, I will fly. So usually we do that kind of stuff. We don't know how it's going to move. English and German have kind of a similar subject, object, verb kind of stuff, right? The ordering. But still we change their position, some of the words. And we do this kind of an alignment between English and French. We say that, okay. So this is the alignment matrix. They say that find the alignment first. And alignment means that sometimes it is different. See, for these 3 words, I have a single word in French. Okay. And usually it goes like a diagonal, but it doesn't have to be diagonal. And sometimes it kind of does this crazy stuff. Okay. He hit me with a pie. I don't know why it is so short in French, and its order is changing, right? And this one is very different, right? The poor don't have any money. So alignment is a little bit different from language to language, and it's a complicated thing. They previously extract this alignment matrix first and do the translation of these phrases one by one. If I do the alignment, then I can do this, right? The less, pores, pore. How do you read this one in French? Anybody know? What, pore? Pore. Okay. And do that kind of translation, and they hope that if you put them together after the alignment, it will work. Well, it works up to 90%, but rest it just doesn't work. Okay. So again, Viterbi is there. Okay. Dynamic programming. But at the end, we are going to do this. We are going to do this. Okay. Sequence to sequence translation. Let me show you that one, and there it is. Here it is. Here. Sequence to sequence translation. Where is my sequence to sequence translation example? Well, you know what I mean, right? You don't? Remember I gave the input to the RNN, and it produced me the tags. Instead of producing tags, okay, it produces the other language. That's the sequence to sequence translation. But for some reason I couldn't find the example. Okay, so this is supposed to be funny. Well, that's how the statistical language modeling works. Okay, that's it for today. I will start talking about these. Arkadaşlar bu şey ne oldu ya? Ne zaman yapıyorduk lisanslı öğrencilerin sunumlarını?